after Brian May and George Smoot. And actually, it's my fault because I was the one to make the program. And I don't know how I didn't realize that what I'm doing actually, the last talk, and my God, it's too late. I can't change it anymore, so I have to take the challenge. And I'll try to entertain you because this is a different talk. And actually, I have to accept it. I did it in 3 hours. This is really the first time I'm doing a talk on this subject. It's why 3 hours? Because I was so busy, I had everything in my head. Never had time to write down the stuff. And this awful design, the design of my talk is really awful. What is important is the content, because we are scientists. You know, we don't care for design. We like the stuff, the right stuff. Okay? So then I go for the right stuff. A stellar orchestra in the acoustic universe. Or let me call it music of spheres. Ancient philosophers from Greece, they were really inspired by, let me call it, a project which was first presented by Aristotle. His idea, his inspiration that perhaps there are some sounds in the universe, in the cosmos, which are triggered by the motion of planets or whatever. He never actually specified how the sounds are produced. It was never clear. But he and many other philosophers, they were trying to find some relationship between kinematics, geometry, or something related to planets, stars, or whatever, and the musical scale. And Kepler was the one who went and said, okay, there is something that I have to, he was a musician. Kepler was a musician. And he took this challenge to discover the music of spheres, because he was very inspired. And by accident, he discovered his 3 famous laws. Well, he was not after that, so he was after music of the spheres. So that's very interesting. And even Fred Hoyle, many astronomers were just looking at how there's sounds in the universe and what is going on, harmony, etc. There's a lot of information in the internet, in books. So I went non-stop on this. And Mike Oldfield was very inspired. So he just produced his latest album 2 years ago called Music of the Spheres. It's not an electronic music, it's a full symphonic orchestra. And many musicians, artists, astronomers, scientists, they are all inspired with this project. And but let me talk about what is the music of the sphere. Are there sounds in the universe? Are there sounds? By definition, a sound is a pressure wave. These are acoustic waves in a gas or in a solid body. And we do have sound waves. We do have sound waves in interstellar medium. In early universe, there were sound waves in disk, in gas disk, in supernovae, in stars, but not in all of them. So apparently, in disks which are around compact objects, some of my colleagues claim that gas disks around black holes or neutron stars, there are many articles dedicated to this subject, they contain acoustic sound waves. How you detect them? You see very fast variability in X-ray, which is interpreted as due to the sound waves in actually in audio domain, and sometimes these are ultrasounds. If you try to play them, they sound something like this. I don't know if this is real or not, but this is what this theoretician claimed it sounds like, okay? So let's step to the next line. And some other colleagues, John Trammell, claims that when the universe was young, there were sound waves, very low frequency, which were playing their music like that. Adam Burrows, just I think it was 2 years ago, when you emailed me sounds from supernovae doing simulations. So he discovered that apparently when a supernovae explodes, I'm not sure if these were type 2 supernovae, type 1A, type 2, okay. Type 2 supernovae which come from the explosion of massive stars. So he discovered that you may have sounds, so it's not just the explosion that you see in all frequencies, but it's also accompanied by sounds. And it's quite amazing because, you know, in astronomy we always see things happening, but there are no sounds. That was it, right? So this is what I got from you. That's it. And you have the explosion. Okay, but it's more interesting if you jump to stars. Why? Because stars, there are so many different kinds of stars, and that's why you have a variety of sounds. So you can have all sorts of sounds in stars. And stars is a typical solar type star with a core temperature of up to 10 million degrees. The atmosphere is cool, 5,000 Kelvin. That's what we call cool. It's a very cool atmosphere. It's only 5,000 Kelvin. And a very tiny atmosphere, 10 to minus 10 masses of the sun. What are we doing? How we discover the sound waves in stars, in solar type stars? This is the spectrum of the sun, what we call the Fraunhofer spectrum, which we've learned from school physics. We actually study the spectra of stars and we compare them with the laboratory data, the frequencies of the spectral lines in the lab. And we see that the positions of spectral lines, they change in time. So which means there is something going on in the stellar atmosphere, right? So these are observations of one of the solar type stars, New Era. You see, this is the rate of velocity derived from the averaging of thousands of spectral lines, because you have to do that in order to have a precision. And the precision you can get with one of the best instruments, actually the best one now, is a HARPS built in Switzerland to discover the extrasolar planets and also do the astroseismology. Precision is, these are meters per second, so this is less than 1 meter per second precision. You can measure the velocities on the surface of stars with a precision less than 1 meter per second. So that's why we can discover now extrasolar planets and Earth-like planets, etc. So those are real oscillations, these are real waves in the atmosphere of the sun. That's what we see. So this is not a noise, this is really a waveform. Maybe there is a little noise here, which we have to filter out, and we do that with the Fourier analysis. So we get rid of the noise, and we clearly see what is the waveform in the atmosphere, right? But the observations are very tough. It's a challenge to do this kind of observation. So this is an example with HARPS telescope, 8 nights of run, observing run. These are 8 different nights. Each night, in total, there are about 2,100 spectra in total. So each night you get a few hundreds of spectra. And you see this change, this is a modulation which is caused by the planet which is orbiting the star. Okay? But during each night we see huge variation in the velocity from spectral lines. So this is all due to the oscillations in the atmosphere which are caused by sound waves. Okay? So 8 days, 80 hours observations of this star. And that's why. But this is Alpha Centauri A. Alpha Cent A, precisely exactly the same kind of variations you see each night. But obviously there is no modulation because so far there was no planet discovered around that star. So you don't see any modulation, but see in each night you see huge variations in velocity. And this is New Era in every night of observation. Okay? So this is not a noise, so these are sound waves actually in the atmosphere of the star. Velocity variations, okay? And when we filter out the noise, this is what we get, what we call a power spectrum. The power spectrum, these are frequencies, very low frequencies, only a few minutes oscillations, okay? And the amplitudes of sine waves that we have to sum up and get this observed waveform, okay? So there are maybe 10, 20, 30 sine waves of different amplitudes. This is a classical Fourier transformation. So we have to sum up and recover the waveform, okay? And that's the same thing we have done for Alpha Centauri A. And now if I keep the waveform and I move it to audio domain, which I can do perfectly because it's the same thing as playing piano 10 octaves down. So I don't change my musical instrument, I just change the frequency, just to be able to hear it, okay? So it keeps, I keep the sound, the timbre, and move it to audio domain, and Alpha Cent will sound like that. Data which is coming from light variations of stars, which are obviously partially and maybe due to the variations of, due to the pulsations, because the sound waves also produce light variations. The problem is we don't know theoretically, models do not give any clear relationship between light and pressure variations, so we cannot easily say the amplitude of light variation, how to transfer this into pressure variation or velocity variation and to produce a sound. This is a very serious problem. It is not answered in models, at least. And theoretically, the relation between intensity and pressure is very complex. And this is a proof that for some stars, I have an example star which was observed with Kepler, the light variation, and transformed into sound. And for the same star, we have a Doppler data, which is velocity variations, which is easily related to pressure, and again converted into the sound. So you can see the difference between these two sounds. This is the light, and this is coming from the velocity data, which is more precise. Obviously, there is a difference in the frequency. I should have shifted them into the same domain, but the waveforms are completely different. They sound absolutely. So this is a classical picture. You imagine the star is not a sphere, as something like this. So you have permanently running oscillations produced by acoustic waves in the atmosphere. And not all the stars have sound waves. This is what we call a Hertzsprung-Russell diagram. So there are some, it's a luminosity against effective temperature or spectral class. There are some regions in this diagram where we have stars producing sound waves. Okay? This is the sun, and that is very interesting. This is the acoustic spectrum of the sun in 12 hours, in 5 days, 15 days, 2 months, and 2.5 years. You can see that it's changing. So the sound of the sun is changing, it's not a constant, it's not the same. And it depends in which day we are going to average it. So my average is 2.5 years, and this is what we call an acoustic spectrum of the sun, and it sounds like this. Very short. Well, this is the sound of the sun. Now, acoustic spectrum of the sun is not that different from the acoustic spectrum of the second string of the guitar. You see the same kind of cone-like structure, the main harmonic and equally distributed second and third harmonics. Of course, the difference is the spacing of frequencies and the amplitude relation. But basically, we have the same cone-like structure. But what makes guitar very specific is that these high frequencies. So these are the frequencies. That's what makes the guitar very, very different. To sound it different. I'm sure Brian May's guitar is absolutely different in this domain. So this is what makes the Red Special very special. Okay? And that is what is about the musical instrument being very specific. Now, what are we doing? Well, actually, what I was doing. I was calculating the frequencies of pulsations from models, from theoretical models, and amplitudes interpolating the data, observational data. We have about 14, 15 stars. Why? Because models are not able to calculate amplitudes of these amplitudes of acoustic spectra. So these are the models. You have seen George was showing amazing simulations of cosmology, early universe. We can do those things, but we can't calculate these amplitudes. I think it's even more complicated than what George was saying, because you really need a very detailed structure, hydrodynamical structure of the atmosphere, etc. So there's a whole complex kitchen in dealing with this stuff. So I had no choice. I had to go for interpolation using the observational data. But if I do that, I can do very funny tests. I can take and compare stars of different masses and their sounds. So I take a solar mass star, 1 solar mass, and 1.1 solar mass star, 10% more, and then I compare their sounds. And now this one. There's very little difference, but it is there. If you can, I think this is for musicians. This test, you have to have very good ears to realize the difference. And now if I compare 0.8 solar mass at age 3 billion years and at 4 billion years, after 1 billion years, the sound is again. Just taking stars of different mass, chemical composition, etc., and compare their sounds. It's very funny, because apparently there are stars which have very similar temperatures, composition, gravity, everything, but their sounds are different because they had different evolution. Evolution of rotation. Rotation and evolution were different. One of them started very fast, the other one started very slow, and that's why today, after 5 billion years, they have different sounds. And this is why astroseismology is proven to be the most powerful tool to deal with the stellar structure. It's actually the most powerful tool we have now in astrophysics. Amazing email I received from Arthur C. Clarke in 2004. I emailed him many years ago that I had this interesting project doing and he responded me immediately saying, wow, this is very interesting, you are doing fine, etc. And then he gave me a brilliant idea. He said, but you know, if you have a binary system, don't you think that the stars will talk to each other because there is a gravitational interaction, and that will change the acoustic spectrum? Well, he's right, absolutely, of course. And you have to be Arthur C. Clarke to have a brilliant point like that. And I said, okay, excellent, then I will do it. So he emailed me this, thanks for your email. And I was really astonished by his response. So I took alpha sen A and alpha sen B. It's a binary system, and try to find the difference. Okay. And alpha sen B. Okay. Moving to stars, single stars. All these are famous stars, Beta Hydrae observations. So let's do an experiment. Let's take one of the open clusters, M67. Is a 5 billion years old cluster, and I have about 100 sun-like stars. I have their masses, I have their everything, all information. They all have the same age because they were born together in an open cluster. So they started to sing together, right? 5 billion years ago, they were born together, so obviously they started to sing together. And I said, okay, let's combine their sounds. Let's see what is coming up. Right, so this is just a fun. Yeah, there's no serious science behind this, but it's just a fun. Oh, amazing! This is the sound of a stellar cluster. 100 solar type stars combined together. There is no phase shift because they were born together, but their masses are slightly different. The thing is, it was not obvious if you add them, will you get a noise or you will get a sound like that. And it's incredible because I discussed this. I asked the question to Brian Eno. I said, do you think if I add all the sounds that I have, I will get a noise or I will get something harmonic? I said, you should get a noise, you should get a noise. I said, no, and I put the sound and said, I'm sorry. Now, the last thing I want to show you, what happens if I bring up the sounds of a whole galaxy, all stellar clusters, because we have information about all clusters, their masses, it's approximately. Now I can do that, I know their mass factors, and I know lots of things, so I can do an experiment. I can add up the sounds calculated because I have those grids, I have a model, so I can add up everything and find the final sound of the whole galaxy, or even the whole universe, if I do some approximations, etc. But for the entire galaxy, this is the most interesting sound, this is the most amazing sound that you get when you add all the stars in our galaxy, all clusters and everything. That just wait to hear the sound.
Now we have time for questions to Mr. Garik.
No? Just one question.
We will... Hi, Brian Matthews, North Wales, UK. Garik, how did you get the data for the sounds that we were listening to of those stars in the sun?
For the sun?
What data are you actually obtaining to extrapolate those frequencies?
Right. The data is available in articles. These are scientific articles for New for Betas, and this is all public data. For those 15 stars, right? The stars which I have for amplitude interpolation.
And what instruments did you use to measure to obtain the data? What instruments did you use to measure to obtain the data?
No. This is not my data. The 15 stars are available. This is observed with Coralie, with Barbs, and these instruments. The 15 stars, my data, my stuff are models, calculations, frequencies, okay? But the 15 stars that I have are observations from different articles.
Thank you.
Any other question? Yes.
show us pulsars, Garik? They would have some interesting sounds, wouldn't they?
Yeah, they sound in radio waves. So those are electromagnetic waves. So I don't consider conversion of electromagnetic waves into sound waves. Because I'm just talking about acoustic waves, sound waves, not a conversion of electromagnetic waves. Because I think if we go for this, we can convert any kind of light into sound. Basically, any really PVC, infrared, gamma ray, whatever I can take and convert this into sound, which I think is a bit, I always consider this a bit artificial, in a sense, because I'm just dealing with acoustic waves. Okay.
Any other?
Hi, that's too much. Sorry, I'm not an astronomer, but I would like to know, I know planets doesn't gives any light outside, but in case that you can measure that anyway, or in a sun, would you think that intelligent technology, like we think we do, or we have, will give any different frequency, any different sound that you can say, okay, here is something completely different of everything I have heard before?
I didn't understand the question, sorry.
My question will be, if you find some place that the sound is completely different because is there an intelligent technology, like
you
for
mean
example,
the star is totally different?
Yeah, or for example, we do like our planet, which will be our sound, like because we have or we think we have intelligent technology, will be completely different our sound. You know what I mean? Sorry. Different
Oh, yeah?
The sound of high technology.
The sound of high
What do
technology.
you think is it comparable to stars? Different?
High technology sound.
What
Right.
sound do we produce? What do we
Well, we don't produce any sounds.
Any other?
No.
I'm so sorry from now. I have learned in elementary school that there is a difference between light waves and sound waves. And one of the experiments that I was shown first was that sound doesn't propagate in empty space, while light does. So, can you explain something about the physics that to explaining the propagation of sound in empty space, which is in the universe?
That's the
Thank
most
you.
common question I hear. That's because people always ask how you detect those sounds because there's a vacuum. So obviously these sounds, we don't hear them here. What we do is we study the pulsations of stars, the atmospheres of stars, and we recover this information using the frequencies and amplitudes of these waves. Basically what we are doing, imagine we are observing on the Earth a volcano on the Mars, and there is an atmosphere. Now you see the volcano effect, but you don't hear it being on the Earth. Now imagine you have a very powerful physics, computers and everything, and you know how to model this. So using the data, spectroscopy data, which the effects that the volcano is producing on the upper layers of the atmosphere, right? And the change of the color in the upper layers because of the temperature change, etc. Using all this information, you can model the sounds that people would hear on the Mars from this volcano. And you are sitting on the Earth and hearing that sound. You can perfectly do that. So this is precisely what we are doing with star sounds. Yeah.
Okay. Thank you, Mr. Garik. Oh.
At 9 o'clock. 9 o'clock.